So in this short video, I'll be telling you a small yet very famous and interesting question in graph theory, which is called the three friends and strangers problem. So here's the problem. Imagine you're at a party and you ask yourself the following question, which is, what is the smallest number of people that must be present at a party so that you're certain there's three people who are either mutual friends or mutual strangers? To make this problem a little bit more abstract so that it's easy to work with, I'll be demonstrating the friend relationship through a graph. Okay. So let's start with a simple case, which is three people. So it's three people case. I'll be representing each people or each person by a node. Let's call them A, B, and C. And for the friendship, I'll be connecting two people by a blue line if they're friends. And I'll be connecting them by a red line if they are strangers. So in this case, because of this counterexample, we already know that when we only have three people at a party, we are not going to be certain that there's three people who are mutual friends or mutual strangers. So three people is not the correct answer. Now let's think about a slightly more complicated situation, which is what if we have four people? Let me give you a specific situation for the friendship in terms of four people, which is this one. Okay. Easily you can see from the graph that there's no blue triangle, and there's also no red triangle. What that tells you is that there's no three mutual friends. There's also no three mutual strangers. And now we know four people is also not enough to guarantee the existence of three mutual friends or three mutual strangers. Now let's move on to five people. Okay. Again, I will give you a situation for which there's no blue triangle nor a red triangle. It's not a very good drawing, but it shows you the point. There's only a blue cycle of length 5 and a right cycle of length 5. Okay. So again, this is not the correct situation. Now let's move on to the case where you have 6 people. Here, I will be doing things slightly different. Instead of giving you a counterexample, I'll be showing you that 6 people is actually enough to guarantee the existence of three mutual friends or mutual strangers. Now let me show you why this is true. So again, let me first represent the 6 people by nodes. Okay. They're kind of positioned in a weird position, but you see why we're doing this. So here you can see that A is connected either through a blue line or a red line to 5 peoples. Then by the pigeonhole theorem, we know that at least 3 of the lines will share the same color. Without loss of generality, we were just going to assume that A is connected to B, C, and D, all in the blue color. So A is friend with B, A is friend with C, and A is also friend with D. So now let's think what's going to happen between or among B, C, and D. If B and C are friends, then we have a 3 mutual friends situation, because then we have the blue triangle, which is A, B, and C. So that's now good. If C and D are friends, we're in the same situation. We have a blue triangle. Similarly, if B and D are friends, we're in the same situation again. So what this tells us is that all these edges must be red, or B, C, D must be strangers. But then what's happening here is then B, C, and D form a red triangle, where B, C, and D are the 3 mutual strangers. And that's the end of the proof. which is quite simple, but yet very powerful. That's how. I hope you enjoyed the video and you enjoyed the problem.